So next we want to start to think about how electric fields and electric forces are generated by different sorts of shapes. So if we know the field generated by a shape, then we can find the force, because the electric field tells us the possibility of a force on a charged particle. So we would take our field and multiply that by the charge, and we would have our force. We want to think about the idea of electrostatic equilibrium in order to better understand how electric fields are generated by conducting systems. Okay, so if there are no electrostatic forces, well, then the electric field must be zero. If the force is zero, then the field must also be zero. That means that inside of a conducting material, once the charges have stopped moving, the electric field is zero. That is because the mobile charges have flowed to counter any net forces, so once they've come to a stop, the field is completely screened, and the forces within are zero. This also results in all of the excess charge in a conductor ending up on the surface of the conductor. If you have excess charge, then the charges will repel each other, and they will then separate from each other as much as possible. If you have a flat surface, then the charge will be evenly distributed at the surface of the conductor, and the electric field is exactly perpendicular to the surface. This is because if you have an even distribution of charge, then there will be a charge on the right that creates a field that points to the left and up, but there is exactly the same amount of charge on the left that generates a field that points up and to the right. So you add them together, and you get a field that points perpendicular to the surface. I've assumed that the charge is positive here, but if the charge on the surface was negative, then the electric field will point straight into the surface. Again, it'll be perpendicular to the surface. So now we want to think about a uniform electric field. This is analogous to gravity that we've talked about a good bit before in 201. In the case of gravity, we consider the gravitational field at the Earth's surface to be uniform. That means the strength of the field is exactly 10 meters per second squared, or, well, I guess it's 9.8, but for this course we'll use 10 for simplicity, and that field is pointing exactly straight down towards the center of the Earth. If you climb up to the second floor of a building, or even climb up a mountain, you will have the exact same gravitational field, and the weight force will be exactly the same. In principle, it varies a tiny bit, but practically speaking, if you climb up the mountain, then the weight's going to be exactly the same on the Earth, because the change in g is negligible, because you're not changing g by any meaningful amount. So that means that the gravitational field is effectively uniform. And because of all of our practice with g, it would be nice to work with some uniform electric fields. To form an electric field, I suppose you could take a charged particle and move some mass distance away, but that's not terribly practical. A simpler way is to make a uniform electric field is to have a large plate and give it a net charge. The charge will distribute evenly over the plate, and this will produce an electric field that is pointing straight out of the plane. That means if we have an infinitely large plate of charge, the electric field is exactly the same no matter how far away from it you are. This can be a bit surprising. Part of the reason is that thinking about infinite systems is a bit intuitive. I suppose one way of looking about it is if you are standing next to an infinitely large screen and you walk away from it, the screen will look exactly the same. It's going to stretch forever in all directions, so it's going to look the same if you are right next to it or if you are a million miles away. With the uniform electric field, the field lines point straight out of the surface, and because they're all pointing straight out of the surface, there is no change in the density of the electric field lines, so the field strength is the same. So the plate doesn't have to be infinite, you just have to be much closer to the plate than the length of the plate, and so in that case the field is effectively uniform. Okay, so a nice example of a uniform electric field is a parallel plate capacitor. Here we have two plates, one is positively charged and the other is negatively charged. So our field lines will point from the positive plate to the negative plate, and the electric field between these two plates will be a constant. This is great because we pretty much have the situation we had before with gravity, except now it's an electric force. If you tilt your head to the left, we have the same situation as gravity because we have a constant electric field pointing left to right. So you probably remember that potential energy with gravity was mgh, and this worked because the gravitational field was constant. Well, inside the capacitor, the field strength is E, so that replaces G. The mass is replaced by the charge Q, and the H is replaced by the distance, so we can get the electric potential energy to be QED inside of the uniform electric field. So that's great, but we need to understand more about how uniform electric fields are formed to do this. So, we need to talk about flux. So flux is a fancy name for flow. So we want to know how many electric field lines flow through a certain area. Maybe an easier way to think about this is to make an analogy with the light that flows through a window. So if you want a lot of light to shine through your window, what do you want? Well, first of all, you want a very bright light source. Secondly, you're going to want a very large window, one that has a very large surface area. And lastly, you want an angle between the window and the source of light to be such that the light is shining directly into the window. That means that you would maximize the amount of light, or the flux of light, flowing into your window. Electric flux works much the same way. The electric flux is EA times cosine of theta, where E is the electric field, so the larger the electric field, the larger the flux. A is the area, so the larger the area that we are considering, the larger the flux. Lastly, we want the electric field lines to flow directly into the area. So to find this, we multiply E and A by the cosine of theta. So the angle theta is the angle between the line perpendicular to the area of the surface and the electric field. So if we are looking at the example on the left, the angle is 0 degrees. The vector for the area is pointing to the right. This is because if we have a plane, what direction is the plane pointing? Well, I can't really pick a direction within the plane because there are 360 different directions that we could all choose. However, the direction perpendicular from the plane is unique, and it defines the direction that the plane is pointing. So if this angle is 0, then the cosine is 1, and the flux is maximum. If we take the case in the middle here, where the angle is 90 degrees, so the electric field is traveling parallel to the plane, then the cosine is 0, and the flux is 0 because cosine of 90 is 0. If it is at an angle, well, then you find the angle between and take the cosine. So remember, the angle we want here is between the line perpendicular to the area and the electric field. I know in one of the classwork questions and homework questions we're about to have you do, we will give you the other angle, the angle from the surface of the area to the electric field. So that means the angle you need is going to be 90 degrees minus that angle. That's going to give you the correct angle between the line perpendicular to the area and the electric field. So, the reason we care about flux is that it allows us to find the electric field in a number of cases. Gauss's law tells us that if we take an arbitrary surface around a set of charges, the electric flux that goes through the surface is equal to the charge that is inside of the surface divided by E naught, which is the permittivity of free space, and is 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. So we've talked about that unit before, and so it's going to make another connection here very soon. That means that to have a flux, there needs to be a net charge inside of our surface. So if we take a charge here and draw a sphere around it, then the electric flux is the electric field times the area of the sphere, and that is then equal to the charge inside of the sphere over E naught. So if you could find the area, for example, you could find the strength of the electric field as a function of the charge. Notice if the net charges inside the surface are positive, then the flux is positive and the field lines leave. If the field lines are entering the surface, then the charge inside is negative and the flux is negative. In the question we have here, there is no charge inside of the object, so with our soda bottle. So that means if there is no charge inside of the object, then the flux has to be 0, right? If Q is 0, then that means that the flux is 0 as well. So that's because every field line that enters the bottle also must leave the bottle, because field lines are only created or destroyed at charged particles. So if there's no charges inside, there's no change in the number of field lines. Okay, so that's kind of a funny example, but if we choose our shapes carefully, we can learn a lot about differently shaped systems, especially when the symmetry of the shape matches the symmetry of the surface that we use. Okay, I think I'm going to stop here for the so-called Tuesday lecture. We'll have a bunch more Gauss's law questions to do on Thursday, and I think we'll be able to wrap up our first unit with a bit more challenging problems. All right, so good luck on the questions, and take care of yourselves.